Okay guys, here we are. We're looking at example 5 and finishing it off from today's work. We're determining the point on the parabola closest to the point 0, 3. So we want to find the point that's on this parabola, on this curve, that is closest to that point there. So we went through this in class. We want the minimum distance from this point to the parabola. That distance is given by this equation, and we even proved that using Pythagorean theorem. So we take one of the points, and we take the other point, which is on the parabola, and we're going to plug it in. So this comes in here, and the other point on the parabola is going in here. So that actually just worked out as x and y. I didn't need to use the subnotation 2 in this case, because there's only one x and one y here. We got two variables, so I need to relate x's and y. And by the way, they did that when they gave us the equation, y equals negative x squared plus 6. We went through, we came up with the distance in terms of x, and then what I did was I did a bit of a logic statement with you. I told you that whatever value of x would minimize this whole thing would also minimize the inside part. So then that's what we do. I just went and worked with that inside part, this part, and I found its critical values. We found its critical values by taking its derivative first and setting that derivative equal to 0. That came up with three critical values, 0 and plus or minus root 5 over 2. In this particular example, we can use the negatives because we're on both sides of the axis here, so negatives work in this question, so we have to keep them. It's an open interval. It's got three critical values. I have to use a chart or a number line to prove absolute minimum. I have no choice. Again, a bunch of people are coming up and saying, but I can tell and I know that, and I get that, but proving it is part of what we have to do for this curriculum, and I have to give marks for it. So let's take a look. I want to prove that I have an absolute minimum when x equals 0, or x equals plus or minus root 5 or 2. So we're going to have to look at that for a minute. So let's take a look. What was my original function? Let's just put that in here so I have it. D of x, what we were looking for was x to the 4 minus 5x squared plus 9 all to the 1/2. That's the original function right out of the gate. I was working with just this, so what I did was I took a secondary form of that and just work with this, because whatever will minimize this will also minimize the above one. So I took this one's derivative, which was 4x minus 10x, 4x cubed. And that gets factored. That becomes 2x, x squared minus 5. We set that equal to 0 for critical values. Those critical values that we come up with are, we've already done this, I'm just repeating, rehashing. And for simplicity right about now, I think I'll just do 5 divided by 2 and do the square root, and it's approximately equal to 1.5. So that's what I'll work with when I need a value. So I need to prove that I've got absolute minimums here and maximums, and I got a lot going on here. If I take a look at just a number line, you're going to tell that I got 0, I've got plus 5 over 2, and I've got negative root 5 over 2. And looking at the original question, if someone asked me what the domain was for this function, so those are all the values of x can be, you know that the domain value is x is an element of the real number. So it keeps going and going and going. So this is what we have here. This is going to positive infinity for x, and this is going to negative infinity for x. So this is just our number line. At these values here, we know that the derivative is equal to 0. Okay? These values. So that broke this up into some interval areas that I'm interested in. I'm interested in what's happening from here to here, from here to here, from here to here, and from here to here. Okay, so those are my different intervals that I'm interested. So I'm actually really interested in the sign of the second derivative in those areas. We really want to know the sign in each interval. So it's getting complicated in here, so I am going to go to a chart. I think that's your best way. I know that some of you find it easier to do the number line, but there's a lot happening here. So I think the charts are best. So I'm going to do my big chart, and I'll come out here, and we'll write our intervals here. So I go from negative infinity all the way up to negative root 5 over 2. And I go from negative root 5 over 2 all the way up to 0. Then I go from 0 all the way up to positive root 5 over 2. Then I go from positive root 5 over 2 all the way up to infinity. And you can tell that what I have here, just moving this around so that you can see it better, these intervals here are corresponding with these intervals here. So now what I'm interested in is the sign of the second derivative. So what's going to make up that sign? The sign of the second derivative is going to be made up of these players. And those players are 2x and, I'm trying to do this so I don't smudge everything. The next one is going to be x squared plus 5. Oh, you know what? I did the same thing I did in class, and some of you are probably yelling at me and trying to get my attention, but it's a video so I can't hear you. But there's actually a 2 in here. I did the exact same thing in class, so that's a 2 in there, which is bizarre because I did it correctly. There, bizarre. So this is going to be 2x squared minus 5. Again, trying to do it without smudging the ink. All of that is going to give me the sign of the second derivative. And that sign of the second derivative will actually tell me something about the original distance in terms of x. So let's see what we get here. I need to pick a value that's between negative infinity and negative 5 over 2. So something between negative infinity and negative 1.5. Because remember, 5 divided by 2 square rooted was 5.6. So I'm thinking like negative 6. Well, if I put in negative 6 for x, I'm going to get a negative. In fact, if I put in a negative for x anytime, I'm going to get a negative. And this is going to be a negative interval as well. This is a positive interval, so this will be positive. This will be a positive interval, so that will be positive. So I saved myself some time there. This is going to be x to the, why do I have an x there? That should be a 2. So what's happening here is I put in a value between negative infinity and negative 5 over 2. So something more larger negatively than negative 1.5. So how about negative 10? So negative 10 here will be squared. It will be positive. This will be, that's going to be positive. Let's put in something between negative 1.5 and 0. How about negative 1? So then that'll be 2. That'll be negative. Let's put in something between here. Let's say 1. 1 worked for us on the other side, so that'll equal negative. And on this side, I'm going to put in something greater, so how about 100? And again, we're looking at something positive here. So the overall sign for the derivative is going to be negative, positive, negative, positive, which means d of x is going to be decreasing on negative infinity to negative 5 over 2, or negative 1.5. It's going to be increasing from negative pi over 2 to, oh, I just did the exact same thing there, 5 over 2, sorry, up to 0. It's going to be decreasing from 0 up to 5 over 2, and it's going to be increasing again from positive 5 over 2, comma, infinity. So what that means is that I'm changing direction from decreasing to increasing here. So if I'm changing from decreasing and increasing, I've got a local minimum at least at negative root 5 over 2, comma, d of negative root 5 over 2. That's a local minimum point. I go from increasing to decreasing, so I have a local max at x equals 0. Not looking for a max, so I'm going to leave that alone. And I've got another local minimum here at 5 over 2, the whole thing square rooted, comma, d 5 over 2 square rooted. Which, if we think about this, so one of my local mins is going to be approximately, so if I put in these values, one of the local mins is going to be, and the d value, where's the d value? Way up here. So I'm going to put in negative 1.5. Actually, you know what? That's going to be harder. Well, I can do it. Negative 1.5. Negative to the 4. Subtract 5 times. Oh, that, yeah, I just don't like this. This is ugly. I'm going to use some algebra to help me here. My calculator is not as sophisticated as some of yours. What I needed to do was, I think I'll do this. Root 5 over 2 to the 4, it's negative, minus 5, root 5 over 2, the whole thing's rooted, squared, plus 9 to the 1/2. So I think what I'll do here, let's maybe take this glare off. I'm going to, this is going to be squared, so the negative's gone. So this is actually going to work out to 25 over 4, minus this is going to be squared, so this is going to be 25 over 2 plus 9 to the 1/2. So it's going to be 25 minus 50 plus 9 times 4, 36, all over 4 to the 1/2. So it's going to be negative 25 plus 36. So 36 minus 25 is 11 over 4 square rooted, which is approximately 1.65. Okay, so that means that this point down here is going to be negative 1.5, comma 1.65. And the other value that I had has a positive. So coming down here, my other local minimum had a positive 1.5. So if I come back up here and if I do a little bit of thinking, that was negative. If I do a little bit of thinking, if I put a positive in here, I'm going to get the exact same value as if the negative, because it was squared, or to the 4. Negative, if I put in a positive value, I'm going to get the exact same value because of the negative squared. So in fact, nothing's going to change here. I'm going to get 1.65 again, which means I have 2 points that give me the absolute minimum distance. So therefore, I do have an absolute minimum because they're both the same value. Absolute minimum occurs, and it occurs twice, when x equals plus or minus root 5 over 2, and is, that minimum distance is going to be root 11 over 4. We could also make that root 11 over 2. And that distance isn't plus and minus, it's just 1. So if we go back and look at the diagram, we'll see that this value here, so this distance can be one answer, and the exact same distance in the opposite direction will be the same answer. And those points that you find there, one of them is going to be negative root 5 over 2, comma, negative root 11 over 2. And the other side will be positive root 5 over 2, comma, positive root 11 over 2. And those would be your 2 points that have the shortest distance between them. Anyway, that's a great question. Notice we need to do some work here because we had 2 locals. Both locals give us the same absolute value. So the absolute value, there is one absolute value, and it is root 11 over 2. Okay, guys, I'll post your homework with this post, and we'll go from there.